Hello everyone. Today we are going to discuss another lecture on compound microscope numericals. So yesterday we had already discussed about astronomical telescope. So we have calculated one numerical on this. So today we are going to discuss another numerical on compound microscope. Compound microscope. Compound microscope. Scope. As we know, compound microscope consists of two lenses, objective lens, objective lens of small focal length, and a eyepiece of larger focal length. If this if this is our principal axis, eye is located here. So the image will form an eyepiece. If we recall, what is the magnifying power for compound microscope, which is it is denoted by capital M, which is M0 into ME. M0 is for objective lens. Magnification, yeah, magnifying power, you can say magnifying power. Just erase this one. Magnifying power for objective lens, whereas for ME stands for magnification, yeah, magnifying power for eyepiece. This we have already discussed in our lectures. So the conclusion is magnification. We know the magnification for compound microscope is it is a multiple of MO into ME. MO is what? Magnification for objective lens, and ME is magnification for eyepiece. Or we can say that the ME is also as treated as simple microscope. Is treated as magnification. Is also treated as magnification. Magnification as simple microscope. All right. So we take an example. If we have a compound microscope, a compound microscope of an objective lens of focal length 2 centimeter. All right, and an eyepiece, and an eyepiece lens, of focal length 6.25 centimeter. Good. Another thing, the length of microscope is 15 centimeter. How far from the objective, or we can say that object, should just rewrite this one, sorry. This is length of microscope, and how far from the objective lens should an object be placed in order to obtain final image at D. D is your least distinct vision, which is 25 centimeter for normal eye. Like also calculate the magnifying power. All right, so we have given a compound microscope an objective lens of focal length 2 centimeter and an eyepiece lens of focal length 6.25 centimeter. The length of a microscope is 15 centimeter, and the question is, how far from an objective lens should an object be placed in order to obtain the final image at D? Okay, also calculate the magnifying power. So we have given what? A compound microscope. If we solve this, firstly write what we have given in question. A compound microscope of an objective lens, focal length given is 2 centimeter, and an eyepiece lens of focal length 6.2 centimeter. Focal length of 6.25 centimeter. All right, and next is length. Length of a microscope is denoted by small l, which is given as 15 centimeter. We will discuss what is length later. And it is asked, how far the objective lens should an object be placed in order to obtain the final image at D. So we need to calculate UO, right? Because it is asked that how far from the objective lens should an object be placed in order to obtain a final image at D. All right, and it is also said that also calculate magnifying power, and another one is magnifying power, and another form is magnifying power. So let's discuss. We already know this is, if you plot a ray diagram, a compound microscope consists of a two converging lens. First one is your objective lens. All right, if you place an object here, all right, suppose say this is AB, a line parallel to principal axis will goes from this point. See, we'll call it a focus for this focal plane, and it is given that FO for this objective lens, if this is objective lens, so FO is 2 centimeter, or we can say that the focal length for this lens is 2 centimeter. And if we draw center up, it will intersect somewhere here. Say the image formed here is B dash A dash. All right, now we have an eyepiece of larger focal length. Sorry, if we intersect here, if a line passes through, if a line passes through like this is a diverging beam, so it will converge somehow here at this point. All right, suppose if the final image be at B double dash A double dash. So question says we have to calculate how far from an objective lens should an object be placed in order to obtain the final image at D. So final image is A double dash B double dash. So final image is this one, which is a VE. Say this is D. It is given in question for a least distinct vision, which is 25 centimeter for a normal eye. All right. We have placed an I somewhere here. This distance is our VO, and this image, the image formed by a focal objective lens, is treated as an object for this eyepiece, and says the focal length of FE is 6.25 centimeter. All right. Say this distance, this image is behaving like what? Object for the eyepiece. So this is, say, this is UE, object for eyepiece. So we know the length of length of microscope. Length of microscope. Length of microscope is the distance between objective lens and eyepiece. Right. So if we see here, this distance is our L, length of compound microscope. So length of compound microscope is nothing but VO plus UE. It is UE. Okay, UE. This distance plus this distance. This is total length, which is given how much? 15 centimeter given. So this is equation 1. All right. For an eyepiece, from question, it is given for eyepiece. From eyepiece, the image is formed at D distance. So for focal length, it is given 6.25 centimeter. UE is our unknown. See, this we don't know this how much UE is. So say the object is UE, which is negative according to sign convention. It is just before the lens, so it is negative of sign, right? So final V is your small d distance. This distance, it is also before lens, so we treat it as negative. So this is 2 minus 25 centimeter. All right. From lens formula, we know 1 upon f is 1 upon v minus 1 upon u. Okay. On substituting the value of 1 upon f is 1 upon 6.25 is equals to 1 upon v is negative of 25 centimeter minus u is positive 1 upon ue. If we need to calculate 1 upon ue, so this is 1 upon 6.25 plus 1 upon 25. All right. So this becomes 100 upon 625 plus 125. If we calculate this becomes how much? U becomes 1 upon 5. Sorry, U becomes 5 centimeter. So we know U is object for eyepiece is 5 centimeter. All right. So now we have to calculate U. We know this quantity. This is how much U is your. This quantity is, this length is 5 centimeter, and we know the L is 5 centimeter. So this must be 10 centimeter. All right. From equation first, we know L is 15 centimeter, which is again equals to VO plus UE. VO is unknown plus U is, now we had calculated 5 centimeter. So if we calculate VO, which is 10 centimeter. All right. So VO is your 10 centimeter. So if we directly take VO is your 10 centimeter. Focal length for objective lens is FO is your 2 centimeter. We need to calculate UO. So from lens formula, we know 1 upon F equals to 1 upon V minus 1 upon U. Okay. So for objective lens, this becomes 1 upon F naught is to 1 upon V naught, 1 upon U naught. All right. So if we substitute the value, okay, so where U naught is negative of sign. Why negative of sign? Because object is placed before objective lens. So this quantity, according to sign convention, this quantity must be negative sign. So this quantity is negative of sign. So 1 upon f is your 2. 1 upon f is your 2 centimeter. And this is 10. This becomes u. So 1 upon u becomes 1 upon 2 minus 1 upon 10. Alright. So UO becomes here how much? If we calculate this, U becomes 5 upon 2. This is 2.5 centimeter. So this what we have asked for. What we have asked for how far from an objective lens should an object be placed in order to obtain an image at D. So we have calculated how much. This must be, the object must be placed at U equals to how much distance? 2.5 centimeter before objective lens. This is one. Another one is calculate the magnification, a magnifying power. So magnifying power of a compound microscope, we know the generalized formula is ME multiplied by MO multiplied by ME. So MO is nothing, VO upon UO multiplied by 1 plus D distance upon FE. This we have already discussed in our classrooms. So only taking direct values of this formula. So substitute here. But we know VO is your 10 centimeter, UO is 2.5 centimeter, 1 plus D is your 25 centimeter, upon FE is 6.25 centimeter. Alright, on substituting, on calculating these value, we will get 100 upon 25. This becomes 1 plus 2500 upon 625. Further calculating this, we will get approx 20. Okay, so the magnification for compound microscope is about 20. Sometimes you can take as a negative also, just because the image is inverted, so the magnification can be negative. It's up to you. You can write positive or negative value. So this is the second needful. So this was our numericals from compound microscope. So we had already discussed about simple microscope, compound microscope, and telescope. Now we take an example. Let's take a new page. Let's take a new page file. New page. There is a question. Question number 2. An object of a telescope is an achromat of focal length 90 centimeter. An object of a telescope is an achromat of focal length 90 centimeter. The magnitude of the dispersive power, dispersive power of the two lenses are 0.024 and 0.036. Okay, calculate their focal length. So this is a question from telescope, but if we know if we read question carefully, it is asking about calculate the focal length of individual lenses. Okay, so we know the telescope consists of two converging lens. All right, but it is in case of achromat. So if we take what we have given is dispersive power, if say omega 1 from 0.024 and omega 2 is 0.036. all right, focal length is given. Okay. Focal length is your complete focal length is your 90 centimeter. If we memorize what achromatic condition for lenses combined focal length is your omega upon f1 plus omega 2 upon f2, which is equals to must be 0. Say equation number 1. If we calculate one of the focal length f2, suppose say we have to calculate f2, so this is omega 2 upon f2 is equals to negative of omega 1 upon f1. If we need to calculate 1 upon f2, 1 upon f2 is 1 upon omega 1 f1 omega 2. Okay, so 1 upon f2 becomes minus, substitute the value of omega 1 and omega 2. Omega 1 was 0.024 and omega 2 is 0.036 multiplied by f1. Say equation number 2. Okay, just simplify. First simplify here. Just simplify this one. This becomes your negative of 2 upon 3 f1. It will cancel from 12. Right. So we know achromatic condition, the separation between two lenses must be 0. So the combined focal length can be 1 upon f1 plus 1 upon f2. It is a case of achromat. So the t is tends to 0. Okay, so we know 1 upon f is given 90 centimeter, 1 upon f1 which is unknown one, and f2 we had calculated in terms of f1 is 2 upon 3 f1. Good. So this becomes, on solving this becomes 1 upon 3 f1. So if calculate f1, so f1 becomes 30 centimeter. And f2 is simply f2 is substitute here in this one. So f2 on calculating f1 f2, so f2 becomes almost 45 centimeter. Good. So this what we have asked. It was a case of a telescope which is on an achromatic condition, and we the question said that calculate the value of f1 and f2. So we have calculated f1 f2. F1 is 30 centimeter and f2 is minus 45 centimeter. Good. So this is the second question. Okay. Suppose we have given another, let's page a new one. Let's take an example 3. So if we have given two thin lenses of focal length f1 and f2 separated by a distance d, have an equivalent focal length 50 centimeter. Now this is a case where the separation between f1 and f2 is given is d. This is not a 0, so we will take a separation between them is d, and we have given an equivalent focal length is 50 centimeter. The combination satisfies is the combination satisfies the conditions for no chromatic aberration and minimum spherical aberration. All right, so we have to find the values of f1, f2, d, and assume that both the lenses are of same material. Either it can be made of a ground glass or a flint glass. So the question, we have the two thin lenses of focal length f1 and f2 separated by a distance d. So we will take a combined focal length as 1 upon f as 1 upon f1 plus 1 upon f2 minus of what, d upon f1 f2. On the last question, we have vanishes this quantity. Why we have vanishes this quantity? Because it is in case of achromat. So but on this question we will consider this one, because it is clearly said in question what the separation between the two lenses is d. Okay, and the equivalent focal length is 50 centimeter. The combination satisfies the condition for no chromatic aberration. There is two conditions. For one is no chromatic aberration and another is minimum spherical aberration. We need to calculate what, f1, f2 and d, and both the lenses are of same material. All right, so let's solve this. If we calculate the equivalent focal length, so 1 upon f becomes 1 upon f1 plus 1 upon f2 minus of d f1 f2. This is equivalent focal length. Okay, just simplify this. We will calculate 1 plus f2 minus d of f1 f2. So this is 1 upon f1, 1 upon capital F. Now the question is no chromatic aberration. For no chromatic aberration is, we know the separation between two lenses must be f1 plus f2 upon 2. This is the condition for, say this is equation 1, say this is equation 2. This is the condition for no chromatic aberration. And another is for minimum spherical aberration. Third condition is for minimum spherical aberration. For minimum spherical aberration must be separation between f1 and f2. This is for minimum spherical aberration. Say equation number 3. So we have three equations. Which one? Equivalent focal length 1 upon capital F is f1 plus f2 minus d upon f1 f2. For no chromatic aberration is d equals to f1 plus f2 upon 2. For minimum spherical aberration is d equals to f1 minus f2. From equation 2 and 3. From equation 2 and 3. From equation 2 and 3. f1 substitute value, f1 becomes 3 upon 2. Okay, and simply f2 becomes here d upon 2. So we can calculate this here. Okay, now substitute the above values values in equation 1. What is equation 1? Equation 1 was 1 upon f, capital F is f1 plus f2 minus d of f1 into f2. Substitute here. 1 upon f is 1 upon 50. f1 is 3d upon 2. f2 is d upon 2 minus d upon f1. f2 is 3d upon 2 multiply by d upon 2. Okay. So on solving here, this becomes here how much? On adding this becomes 4 to d upon this one. So simply we can find this is d becomes 200 upon 3. On dividing this we will get 66.67 centimeter, something like this. Okay, if we know d, this is 1 over, we have to calculate d. Now we have to calculate f1 and f2. So f1 is what? f1 is 3d upon 2. f1 is 3d upon 2. Substitute here. So this is 3 into d is your, if you say this quantity, this becomes 200, or simply just write, remove this. 3 upon 2, d is 66.67. Just multiply that. It is approx 100 centimeter. Okay, approx. f2 is just d upon 2. d upon 2 is 66.67 upon 2 is approx 33.3 some centimeter. This is approx. So we had calculated what? Small d, f1 and f2. So this is how we will calculate d1, d2, sorry, in d1 and f1, f2 with the help of what we have given, with the help of equivalent focal length, in condition for no chromatic aberration, and for minimum spherical aberration. So these are some numericals based on our geometrical optics. So we have discussed today what? One numerical from compound microscope, one numerical from aberration, another one is from aberration. So we will continue our numerical series on our next lecture. Thank you.